Today's topic is zeros of analytic functions and the relations between zeros and poles. We are going to first look at zeros and zeros of analytic functions. Okay, here residues. Okay, before going further, here we review poles of order m. In the previous section, we have learned this notion when we dealing with three types of singular points. We have studied the poles of order m. If the principal part of f at g0 contains at least one non-zero term, but the number of such terms is only finite, then there exists a positive integer m which is greater than or equal to 1, such that bm is not equal to 0 and bm plus 1 and bm plus 2, every bm plus k, where k goes to infinity, is equal to 0. Then we have this form for the function, given function f, because if f has an isolated singular point at g0, then f of g has a Noether series representation like this, given by this formula: positive powers plus negative powers part. With this condition, infinite number of bm plus k are all zeros. So in this expression, only the finite number of terms, m terms here, arrive, except that infinite number of terms are 0. Here bm is supposed to be is not equal to 0. In this case, we called the isolated singular point g0 is a pole of order m. Okay? A pole of order m is equal to 1 is usually referred to as a simple pole. Okay, this is the notion of poles of order m. Zeros and poles of functions are closely related. So we are going to see how zeros can be a source of poles in section 83, zeros and poles. Now, before study this, the relation, we are going to study some preliminary results regarding zeros of analytic functions. Okay, let's suppose that a function f is analytic at a point g0. Then in section 57, theorem 1 says that all of the derivatives f and derivative of f of g exist at g0. This is the definition, we can reduce this fact from the definition of analyticity of a given function f. If f of g naught is equal to 0, and if there is a positive integer m such that and m's derivative of f at g naught is not equal to 0, and each derivative of lower order vanishes at g naught, okay, this means f of g naught and the first order of f of g naught, the second derivative of f of g naught, and m negative 1's derivative of f g naught is equal to 0, but m's derivative of f at g naught is not equal to 0. Okay? Then f is set to have a 0 of order m at g naught. This is the definition. Okay, to capture this notion, let's consider a toy example. So let's suppose we have f of g is a2 times g negative g naught to the cubed. Okay, then we consider the m's derivative. In this case, we consider m is equal to 3. Okay. Then f of g naught is 0. It is easy to see that because we just g naught in the place of g, then we get 0. And then we compute the first derivative of f of g naught at g. Then we have this quite basic derivative method. Then we compute the f prime of g naught is 0. Here, if we insert the g naught here, then we get 0. And next, we consider second derivative of f of g, which is equal to 2 times 3 times a2 times g negative g naught. Then second derivative of f g naught is equal to 0. It is also quite easy to see that. But when we evaluate the third derivative of f of g is constant here, 2 times 3 times a2. Here we assume that a2 is not 0. And constant complex number. So here third derivative of f of g is not equal to 0. So here is an example for this function to satisfy with this condition.